in this, when I look at NMR, to some idealized stuff. That's basically my simulations here that I showed. So some old and some new, in particular some new ones. There will be two major take-home messages. In between, you will hear me a little bit ranting. Forgive me when it's getting too much. See, now I have the wrong. Here I am in the right. I need to go to my PowerPoint. And I want to see, this is now. How do I get into my PowerPoint to be able to, good. Just the common slide to do a little bit motivation why I show you something about SICO and SICN. In the sake of the further time of this presentation, I'll skip that. You know this all much better than I do. When we do polymer pyrolysis, some of our so-called ultimate questions is, does the structure of a precursor matter? Yeah, some folks would say, based on thermodynamics, in the end, if you go to high temperatures, it does not matter. Others say, oh, no, it will matter, in particular because in between the kinetics of your polymer structure, in particular, those kinetics may impact what you get in the end, and by this side way, have an impact on the outcome and the thermodynamics of the final product as well. So that's the ultimate question. Does it really matter? Or maybe much better, which property is impacted in which way and how and so forth. And yeah, you see my standard system, some polysiloxanes and polysiloxanes that I model. A little bit more humble, that's basically my part, is what kind of reactions do occur. And I talk here really about chemical reactions. You will see a couple of very fundamental chemical reactions very soon. And of course, at every time, the question is, maybe we are asking not enough this question. What connections can I do to experiment? Do I just make wild predictions, which is always easy as a computational guy, so to go where nobody else was going before, because there is absolutely nothing. But essentially here, and in my case, sometimes we'll talk about mass loss, structure, and fragments, and compositions, and we have done a couple of things in the last 25 years there. And you will see a little bit more on that. Last year, here, same thing. This was one of the final slides after I showed you a couple of things. The outcome was, in our polymers, when we do this simulation of reactions, but also when we do experiment, we learn there are some fast early reactions going on. For instance, you remember this from all the TGA stuff, you observe cross-linking. From whatever you learned in NMR, you learned, oh yes, randomization of your silicon environment, for example, in polysiloxanes, that you get all those mixed tetrahedra. And then after this, there are some slower processes following. For example, carbon segregation, where we see the development of some Raman peaks only at temperatures, let's say 800 or 1000 degrees C, and other stuff has happened earlier. That's basically where we say, oh yes, lower temperature, these are much faster reactions than at higher temperature. We have much slower reactions. Yes, and some of them, well, don't care whether there's lots of hydrogen still left in the system. Carbon segregation, I basically claim, only happens when most of the hydrogen has already left the system. Not all, but most. In one of the last questions, I then said, well, what is about this so-called Kumada rearrangement and then the so-called Kumada type or Kumada-like rearrangements? Kumada-like is the insertion of a carbon into the polymer backbone, for example, in a polysiloxane, or the insertion of carbon in a polysilane to make you a polysilane in this, or polycarbosilane whatsoever. And of course, they are observed everywhere. And how do this mixed tetrahedra develop? This is a fundamental process that changes a lot of the stability in our polymers and is worthy to be investigated. So essentially, that's what I show you today. A little bit about Kumada, the original Kumada process, proposing a new dominant mechanism. Then I'll show you one example of Kumada light rearrangements. We have seen, well, tons of them. Just 3 slides about some new polysiloxanes. And so then something where I tell you, oh, that's where we failed. I hoped last year that we get there, but after 2 years, basically, we went say, nope. And I show you the last is a little bit of ranting and how do things a little bit better. Good. First, Kumada rearrangement. Since I was asked to do this rather quickly, I forgot to include citations. Now, this goes back to 1958 about the original citation or original work of Kumada, which, by the way, has never since been communicated in literature as being repeated and reinvestigated. So this is, take it, 65 years old stuff. We have the, what is this? The bis-trimethylsilane or whatever you call this, or disilane, yes? So silicon with the 3 methyl groups. You start with a gas of this, and in the end, in your mass spec, you observe this, where the carbon has inserted between the 2 silicons, and now you have an Si-Si bridge. The proposed mechanism is what you see here. Every theoretical chemist is either now going to twitch in his heart or first says, oh yes, of course. There's a methyl group switching over and is going to insert into the silicon-silicon bond. Here you see, don't take it too seriously that this is a 5-coordinated transitional carbon. This may happen in particular if this proton is early on switching to the other silicon, yes? So this might happen. This is what you find, I do not know in how many publications, as the proposed and repeated mechanism. Because this is all based on input, observe output. How do I infer what's happening in between? Nobody has seen that. So you have to come up with a good guess. Although there's 65 years, there is even no published computational or theoretical study on this mechanism. If you want to do this, you find that this is at least a transition state of 2nd order, maybe one of 3rd order. I'm not so sure because I gave up. I don't have the time to do this. I put this into the computer in, admittedly, only denser functional theory ab initio simulation, and found this mechanism. I will go through this in detail. The most important thing is you have the development of silane, 2 connected silicon in between. This is finally going to insert in one of the CH groups, yes, correctly, and producing the same outcome. We have observed this mechanism, let's say order of 10, I think 10 or 12 times. We have never observed this. We tried to replicate this by standard Gaussian molecular calculation using whatever method you cannot even offer. We were not able to create a stable intermediate there. What is the detail? We start with our disilane. You will see this. This is what we get in the end. So we start with this. And the first thing that we always observe is abstraction of one of those methyl groups. Yes, it gets very long, this bond. This is one of the early processes. And it looks to me that in most cases, this methyl group is immediately rebonding to this Si. And this Si here happily strays away. You see it in this picture here. These are all snapshots from some almost nanosecond long simulation, which is typically 1 million time steps in this range. Okay, so here we have a tetramethylsilane happily hanging around, and then once in a while they meet again in space and they come closer. By the way, if this guy here hits a different disilane, you will start to create a polymer. This is what Kumada has also reported, that there are more long chain polymers. So that's part of their study as well. But the essence was, how does this carbon insert between the two silicons? And the point is essentially, it's not the carbon that inserts into the two silicons, but it is this silicon which reinserts in one of the CH bonds here. Basically, you see there has activated this and then has created our final state. Okay, that's the first take-home message. Please, for practical purposes, this is absolutely first of no essential thing. It's just a different mechanism that produces the same outcome. Now, of course, for practical purposes, chemists could think to start, okay, what is now the impact of different side groups on this mechanism that make it either easier for the silane to be created or more difficult? Now, Kumada like rearrangements in, we have taken examples from the Durazine 1800 simulations that we were. I have a video of this very soon. They typically start with some H is being transferred, so that your CH3 in the beginning becomes a CH2. Whether this is now a radical or whatever is going to happen, in most cases, the silicon that is attached to this now creates a temporary double bond to this carbon. So you have two H's which may have, like in this case, bond and H2 in between. This is only a very particular outcome. In many cases, the proton has hopped also to other parts of the same polymer or even to a different polymer strand. So it's not always creating an H2. However, this is a dominant intermediate situation that is actually relatively long living in the simulations that happen at 2000 or 2100 Kelvin for up to half a nanosecond in that. Good. And then essentially what we observe in one moment is that the SiN bond here starts to break between one of these three coordinated silicons and its adjacent N. And essentially here, this is now the time for our carbon to insert and finally form the link after this Kumada-like insertion. And the double bond in this particular case has been transferred now from one silicon to its adjacent silicon, so to the next group after the CH2 insertion. Here, in total, it's a little bit lengthy. You see the simulation. Please watch at these two folks here. This is the silicon. This is very soon after some time the nitrogen. And here we have our central candidate, our carbon, which is soon going to produce, come on, yes, now it's the CH2 that is run away. And you see nicely the three coordinated silicon, the two coordinated carbon. So here's formally a double bond. All these bonds that are located here are only indicative of distances, have nothing to do with bond order or whatsoever. And this is rather stable, wriggles around. Yes, so everybody wiggles around. After some time now, if we are patient enough, we will see that this bond is going to break between the silicon and the adjacent nitrogen. And then basically it will be this carbon that flips over. And see, I did not want to break interrupt this in between, and because otherwise nobody would believe me that this is such a very stable state in these kind of simulations that are going to happen. Come on, now it's the time. You saw it already once, you saw it twice, and good. Finally, yes. Now this is in the computer. You see the outcome of this very fast. It's very difficult to make this kind of video, or at least for me, it's very difficult. I'm pretty old. Number two, there are approximately 300 other atoms wiggling around. So to focus on those atoms that are important takes a little bit of additional coding, which atoms to include in the simulation and so forth. Okay, come on, we got you. A few more polysiloxanes. Oh, we made simulations here with this polydiphenyl siloxane, and I do not want to bore you too much about this model where I usually say you don't see anything, you don't see much of a detail there, only that it's nicely rotating. However, in these simulations, we see the beginning of the linking between those benzene groups or phenyl groups, essentially. We come in the end, that's being probably next year being finalized. This is a different mechanism of carbon segregation in comparison to other systems. So carbon segregation here happens differently than in aliphatic side groups of polysiloxanes. The most important thing here is, and sadly, Yigal Bloom is not here because we had tons and tons and tons of discussions as to whether we will see a Humada-like rearrangement in phenyl-based siloxanes where there are no methyl groups to insert. And at least for practical purposes, the outcome, first of all, NMR shows us this is there, yes, but for practical purposes, we have this here as well. Here is one carbon that is between two blue silicons. There is one in there, and we find, if I'm not mistaken, here's a second. Yes, the big fat carbons are always between the silicons. So these carbons do insert there. There are mechanisms that the phenyl groups are disrupted and provided carbon to the siloxane group. So in the end, this is the polymer backbone. Things happened. Come on, everybody, wiggles here. Then a very nice object to study in the computer, something we did over the last year, are these polysealer ethers. I can only recommend anybody. They are now being cited in certain reviews since 20 years as potentially very nice systems. I can only recommend the experimentalists to go ahead and synthesize them. Polysealer ethers, you basically see that the backbone is something like a mixture between a polysilane with Si-Si-Si bonds and a siloxane. Once in a while, you have an SiO bond included as well. Yes, some Chinese have done this 20 years ago, and you always find one or the other paper every other 5 years. The good thing in this is they disproportionate after some time, even in the computer at relative low temperatures. For our purposes, relative low temperatures. Here you have seen what you meanwhile see a pure Si strand of the polymer, and here this is an SiO siloxane. So basically, what previously was a regular chain of SiO, SiO, and so forth, has now disintegrated. And how quickly it does this seems to depend on the amount of hydrogen attached to the silicon, because they mediate quick bond insertions, opening of Si bonds in some cases, and reorganization of your polymers. Where we failed, very sad story, because I prepared the student that he may be up to a misery. So it was 2 years of parameter optimization, coding, so-called machine learning and other things. We were not able to develop a React force field for polysiloxanes, so for the SiCNH. We may have been successful with getting one for SiCOH some 6 years ago, but doing the very same thing on SiCN did not work, although meanwhile we can do it better and blah, 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 and so forth. No. Outcome. You can, in this stuff, always map DFT data onto React data, which means you come from one frame to the next one. You can model any kind of heater formation, reaction enthalpies, so static structures perfectly. Bulk modulus, elasticity, vibrations. Oh, you get this. Great, yes? Everything that is close to a local minimum, you get great. When it comes to the question of modeling transition states. Turns out that you have to model one transition state after the other to include this into your set. And then it gets painful. And the point is, our experience, you cannot just include enough of these transition states in these 3 or 4 component systems. Meaning the other way around, that anything that you do in React also finds its merit in DFT calculations is not true, or in better way, this for this SICN, it has not yet any predictive value. Whatever you do, despite all so-called active learning, including the miseries like 8-fold coordinated carbon in between, back into your training set, there's always something new popping up when you do this kind of simulations. It's horrible. So the student has graduated with completely different material, and this was also part then of his written thesis, never been published, but it's a definitely failure. So what have others do? This is now the German professor. Forgive me, too much German. Maybe I do not know whether Ralph ever encountered Rüdiger Kniep or some of these folks who took a liking to trash other land. I don't want to go too far here, please. Yes. Recently, you have seen a series of publications using the React potential for the simulation of pyrolysis of SiCO. I have to say that I have not been the review of any one of them. Otherwise, even a dumb eye, and I say this here very clearly, would recognize that there's something foul with what you see in those figures. This is what the group has published as a function of time. Here you see the composition fraction, this stuff, and here you see the yield of the mass loss, essentially. So, if you just do a back of the envelope simulation or whatever, you realize that within a fraction of time, here this in the green curve, it's the strongest one, the system seems to throw away all of its mass. It's combusting catastrophically. Now, none of the high explosives that they have ever simulated with React simulations has shown such a behavior. You don't have this incredibly fast bond rearrangement. It's not there. So why the heck could they publish this? Do not know. Maybe folks are just not experienced. You see here even one book, here, one book. Huh? Good. Good. Series of papers there with catastrophic mass loss. Don't want to go much into detail, but first time we reported this 5 years ago at the MSNT, but then this data that you see here has been communicated in a series of talks. Some of them are available, recorded online. So the persons who attended even some of these things, so that stuff has been shown to them. And you see there, I went there a couple of years earlier. So I basically showed, and we have this catastrophic behavior. All these curves, you have changes in a fraction of a nanosecond, or let's stay within 1 nanosecond. And I've never published this. This manuscript is old. This is 2 years old. And then I realized what's wrong. So it was never sent out. Here is something that is incredibly important that the authors do not mention in the description of their simulations. You don't find this in the paper. However, I claim very likely they have used this because this is one of the standard things that is included in the package. Number 2 shows exactly the same as I did. Not exactly the same, but pretty much the same. So what's wrong? This here refers to the charge equilibration procedure in this React force field that is done every 5 steps, meaning if you have a time step here of 0.2 femtoseconds, the charge is only equilibrated every nanosecond. And that's just not good. How can you make it better? I will quickly skip over those slides.
10 minutes over.
Yeah. Pardon me?
10 minutes over.
Good. Free carbon in these systems does not build up even after 10 nanoseconds if you do this with a proper time step and a proper state of your charges at an even higher temperature as they do in those simulations. There's nothing. Yeah. So whatever they saw is an artifact of their choice of parameters that they decided not to do properly. The person who published those papers was present last year when I gave that presentation. She even invited me to give that presentation and has published her stuff afterwards. Where does the free carbon build up? Now, when we looked at all of these structures, we typically look only where the carbon is. And I decided after some time to look at these pink balls. This is where the oxygen sits. And we get a glimpse of this. In the beginning, all the oxygens in our systems are, let's call it, homogeneously distributed. But then we know from some of great NMR simulations and then reverse Monte Carlo simulations of Sabayashi Zen that, oh, this is a fractal structure soon developing in your SiOs, which is also an older story of SiO2. So in the end, it means that your SiO tetrahedra or your SiOC tetrahedra, they pack much denser. And you quickly develop cavities in your structure. And now you can have a long discussion about the chicken and the egg. What is going to form first, the free carbon or the cavity? Based on the story of silicon, others, and I would claim my simulations, I would say, it seems to be the cavity is there earlier. And only when the cavity is there, your so-called free carbon precipitates in those cavities. You see here a little bit of that, and I'll show you now last slide where you see it a little bit more pronounced. This here was all at 2000 Kelvin. Then, pardon me? Excellent question. 4 nanometers. Here you see this up. Now this is being sped up to much higher temperatures. Every 100 Kelvin, we have approximately a factor of 2 in our rates. So what happens here at 2300, we have approximately 10 times, maybe even 16 times faster rates. Simulations, nevertheless, take about half a year. And here is the whole thing with all the oxygens. And here you see, this must be the carbon. Here I left out all the oxygens so that you see there only the carbon. The big blue balls that you see there are silicon atoms that are part of your amorphous matrix, so the SiCO, and at the same time also bind to your free carbon. And you basically see that some of this so-called free carbon does not have a silicon that is attached to this, and you can start to speculate over, is this segregation of the carbon more a phase, so a gas phase decomposition initially, or is it already starting to percolate in the structure as a larger unit and then forming together? I leave this to further times when we have done more simulations on this. However, the important part is it takes an awful long time, this so-called free carbon. We think we are reasonably motivated to claim, based on these simulations, that the SiCO polymer coagulates, forms areas with higher and lower density, call this a cavity. We open those cavities, and in those cavities, the carbon-carbon bond formation happens not inside the bulk as much, but in those cavities. There, the show goes. And I thank you and the sponsors and everybody else for your attention. And please apologize.
So maybe one question, a very quick one. So the calculations you showed are realistic in terms of an experiment, in time scale, I mean, in terms of an experiment, or I'm not an expert in theory. Or
Okay, here's what I often say. Can you do pyrolysis at 2000 or 2300? And I say, absolutely, use a laser flash experiment, but please characterize this afterwards.
Yeah.
And I think here we have a little bit of an issue because yes, you can do it. And even I have done this sometimes ago to construct, to make some nanoclusters, but the characterization of an SiCO with laser, I've never seen that yet. So in principle, it could do. So I feed it back to the experimentalist. Hey, come on, this is a simulation, do the experiment, yes? But in comparison to what you have seen before, this catastrophic behavior, we can show this is a different chemistry that you have in the other simulations. You throw away certain bonds very early on, and this is missing in the end. And everything else seems to be on a time scale 100 to 1,000 times faster than in the simulations that we do. So good.